Right now, across the planet, billions of us are performing a seemingly weightless, silent act. We are hitting the delete button. With a casual tap, we erase terabytes of emails, clear gigabytes of storage to make room for more, and ditch countless old photos into the digital void. The act feels abstract, a ghost in the machine vanishing into an intangible ether. It is an act of pure logic, of symbol manipulation, seemingly disconnected from the hard, physical world of energy, mass, and temperature. But what if that assumption is fundamentally wrong? What if every single deletion, every discarded bit of information came with an inescapable physical cost, a tiny, non-negotiable tax paid directly to the universe itself? What if every single act of forgetting, of unknowing, generated a real, measurable quantity of heat, imperceptibly warming the very fabric of space-time with every keystroke? This isn't some late-night philosophical pondering or a metaphor for digital clutter. This is a fundamental law of physics, a deep and unsettling truth whispered by the very architecture of reality. How can an invisible, immaterial act like deleting a digital bit of data impose a thermodynamic burden on the cosmos itself? To unravel this, we must journey back to a 19th century thought experiment that haunted the giants of physics, a paradox involving a tiny, intelligent being known as Maxwell's demon. In 1867, the physicist James Clerk Maxwell imagined a tiny container of gas separated by a wall with a minuscule, frictionless door. He then imagined a demon, a being small enough to see individual gas molecules, controlling this door. The demon's job is simple. Whenever a fast-moving molecule approaches from the left, it opens the door to let it pass to the right. When a slow-moving molecule approaches from the right, it lets it pass to the left. Over time, without doing any apparent work, the demon sorts the molecules, making one side of the container hot and the other cold. This process, if real, would be a thermodynamic miracle. It would decrease the entropy, or disorder, of the system, seemingly for free. It would violate the sacred second law of thermodynamics, the ironclad rule that the total entropy of an isolated system can only ever increase. For decades, this paradox stood as a profound challenge to our understanding of the universe. It suggested a loophole in the fundamental arrow of time, a way to unscramble the cosmic egg. The resolution, however, was as subtle as it was revolutionary. Physicists, including Leo Szilard and later Leon Brillouin, began to realize the demon wasn't getting a free lunch. The critical flaw in the thought experiment was ignoring the demon itself. To do its job, the demon must first gather information. It needs to measure a molecule's speed and position to decide whether to open the door. This act of measurement links the demon's mind, or its memory, to the physical system. But to continue sorting, the demon must eventually clear its memory to make room for new measurements. It must forget the state of the previous molecule. And it is here, in the act of erasing information, that the cosmic bill comes due. The act of deleting a measurement from its memory, of resetting its mental slate, was found to require energy and, crucially, to dissipate a corresponding amount of heat into the environment. This dissipated heat would always be at least enough to offset the decrease in entropy from sorting the gas. The second law was safe. The universe's books were balanced. But in saving thermodynamics, science had stumbled upon something far more profound. Information isn't just an abstract concept. It is physical. It is tied to energy and entropy with the same unyielding logic that governs stars and atoms. The ghost in the machine, it turns out, has a thermal shadow. This revelation sets the stage for our modern dilemma. We no longer have a single demon sorting molecules. We have built a global civilization of electronic demons, trillions upon trillions of transistors in data centers and devices, all constantly measuring, processing, and, most importantly, erasing information on an unimaginable scale. Every time we format a drive, clear our RAM, or overwrite a file, we are forcing countless microscopic systems to forget. And if the solution to Maxwell's paradox holds true, each of those acts of forgetting is contributing to the universe's thermal budget. This isn't about the waste heat from a processor's power consumption, which is a massive but separate engineering problem. This is a deeper, more fundamental cost baked into the logic of computation itself. So, the question sharpens from a historical curiosity into an urgent modern inquiry. What is the precise physical price of a single erased bit, and what does this cosmic tax mean for the future of information, technology, and the ultimate fate of the universe? From that mind-bending paradox of a heat-generating memory emerges a profound and elegant truth, a principle forged at the very intersection of information theory and thermodynamics. The answer has a name: Landauer's Principle. Proposed in 1961 by Rolf Landauer, a brilliant and iconoclastic physicist working at IBM, it provided the first rigorous quantitative answer to the question of information's physical cost. Landauer was wrestling with the ultimate physical limits of computation, and he realized that the key distinction was not between processing and storage, but between operations that are logically reversible and those that are not. A reversible operation is one where you can always deduce the input from the output. A simple NOT gate, which flips a 0 to a 1 or a 1 to a 0, is reversible. If the output is 1, you know the input was 0. In principle, such an operation could be performed with zero energy dissipation. But many computational steps are irreversible. An AND gate, for example, takes two inputs and outputs a 1 only if both are 1. If the output is 0, you have no way of knowing if the input was 0, 0, 0, 1, or 1, 0. Information has been lost. Landauer identified the most fundamental irreversible operation of all: erasure. The act of taking a bit whose state could be 1 or 0 and forcing it into a known definite state, like resetting it to 0, is the ultimate act of information destruction. Landauer's principle gives this act a precise physical price tag. It states that the minimum energy that must be dissipated into the environment as heat to erase one bit of information is equal to. Let's dissect this deceptively simple formula, for within it lies the entire story. The K is Boltzmann's constant, one of the fundamental constants of nature. It acts as a universal conversion factor, bridging the microscopic world of particle energies with the macroscopic world of temperature. The T is the absolute temperature of the system, measured in Kelvin. This tells us the cost is not fixed. It depends on the environment. Erasing a bit in a colder system is cheaper, thermodynamically speaking, because the burst of heat is more noticeable against a quiet background. In a hotter, more chaotic environment, it takes more energy to make the erasure stick. Finally, and most beautifully, there is Ln, the natural logarithm of 2. This is the pure mathematical signature of information itself. It arises directly from the fact that a bit has two possible states, a binary choice. If we were using a 3-state trit, the cost would be Ln3. The physics is directly reflecting the underlying logic. For decades, this principle was a cornerstone of theoretical computer science, but remained a thought experiment. The energy involved is astonishingly small. At room temperature, it's about 3 × 10 to the negative 21 joules, trillions of times smaller than the energy your eye detects from the faintest visible star. Measuring it seemed impossible. That changed in the 21st century. In a landmark 2012 experiment published in Nature, a team led by Antoine Berout at the University of Lyon, France, finally captured this thermal ghost. They created a physical bit using a single microscopic silica bead just a few microns across, held in a double well potential created by highly focused laser beams, an optical tweezer. The bead resting in the left well could represent a 0, and in the right well, a 1. By carefully manipulating the laser trap, they could push the bead from one of the wells over a central energy barrier into a single combined well, effectively resetting the bit to a known state without knowing where it started. They had erased one bit of information. By meticulously tracking the bead's erratic motion, they could calculate the infinitesimally small amount of energy transferred to its watery surroundings as heat. The result, averaged over many trials, matched Landauer's prediction with stunning accuracy. Then, in 2016, an experiment reported in Nature by a team at the University of Augsburg and CEA Grenoble pushed the verification into the magnetic realm, which is closer to actual data storage. They used a nanomagnetic particle whose magnetic orientation or spin could point either up or down, representing a bit. They applied a carefully controlled magnetic field to flip the spin to a designated down state, thereby erasing the prior information. Again, the measured heat dissipation precisely matched the limit. Landauer's principle was no longer just a theory. It was an observed, experimental fact of our universe. The consequence of this is as profound as it is inescapable. As our digital universe explodes with zettabytes of data, every single deletion, every formatted drive, every reset circuit contributes bit by bit to the universe's total entropy. While the heat from a single deleted file is negligible, the cumulative effect from a global network of data centers processing exabytes of information sets a hard physical floor on the energy efficiency of future computing. It tells us that our quest for faster, smaller computers will ultimately slam into a thermodynamic wall built not of silicon, but of logic itself. This cosmic tax, paid not in currency, but in irreversible thermodynamic change, solidifies the notion that information is a fundamental physical quantity woven into the fabric of reality alongside matter and energy. The heat death of the universe, that far-off state of maximum entropy where all useful work ceases, is often seen as a slow, natural decay. But Landauer's principle reveals that our information-driven civilization, in its very act of thinking, processing, and forgetting, is an active participant in this cosmic process. Every click of the delete button is a tiny, infinitesimal push on the universe's great thermodynamic flywheel, accelerating its journey towards ultimate equilibrium. Our digital footprint is not just on the cloud, it is a permanent thermal scar on the cosmos itself.